Hello and welcome to the webinar, The Future of Aviation, Opportunities in SAF, Hydrogen, and Electric Aviation. My name is Chris Robinson, Senior Director here at Lux, and I'll be moderating today's session. Presenting today is my colleague Runil Dalia, Principal Analyst here at Lux Research. Throughout the webinar, you can type any questions you have in the questions box on your screen. Time permitting, we'll answer all the questions that we can. If your question does not get answered, please don't hesitate to email it to questions@luxresearchinc.com and we'll respond. Let's jump into the presentation. So over to you, Runil.
Great. Thank you very much, Chris. And good morning, good afternoon, and good evening to whoever is dialing in on this webinar today. Very happy to be here to discuss the future of aviation, but more specifically looking at how the aviation sector could reach net zero emissions. So the focus of the webinar will be specifically on technologies, sustainable aviation fuel, hydrogen, as well as electric aviation. But before we take a deeper dive into these technologies, I want to take a step back and look at how the aviation sector could evolve in the future. Now, what you see here on this figure is the passenger count globally. Now, in 2020, for obvious reason, the passenger count was quite low. This was because we had the COVID pandemic. But you can see that projections for 2025 say that we will go back to where we were before COVID. So before COVID, in 2019, we were at around 4 billion passengers, and we will reach that number again in 2025. But what's really interesting is what happens beyond 2025. And you can see that in this case here, the number of passengers is set to grow to almost to 8 billion passengers a year. And this growth is really driven by developments in Asia as well as in Africa. Now, together with that growth in global air passengers, you also have an increase in CO2 emission. Now, what you see here on the orange line is a projection of CO2 emissions, assuming that we make no efforts to reduce these emissions. Now, today, we're at around 2,000 million tons of CO2 emissions. If we keep on going as we are today, then we'll reach around 3 billion tons of CO2 emissions. However, there are initiatives globally around making sure that this does not happen. And one of the major initiatives is the one that has been undertaken by the IATA. Now, the IATA, they are a global trade association. It's the world's largest association of airlines. And the IATA has over 300 airlines from more than 120 countries. Now, a couple of years ago, the IATA have reached an agreement. And this agreement from the different airlines say that they will do the best in order to reach net zero emissions by 2050. So this was a very big milestone in the aviation sector because now you finally have a target for net zero emissions, and that target is 2050. Now, after announcing that pledge, it is now every airline's responsibility to take measures in order to reach that target by 2050. Now, as mentioned before, the IATA is a collection, a very large collections of airlines all around the world. And you can see the different airlines that are part of the IATA. So you have some very big airlines like Delta, Lufthansa, British Airways, and you have some smaller airlines like Air Mauritius, for example. Now, each of these airlines, they have to implement measures in order to reach carbon neutrality. So how does that look for a specific airline? Now, for this presentation today, we'll focus on British Airways. Why British Airways? No particular reason other than British Airways is one of the largest airlines in the world and also one with one of the largest networks of destination. So let's take a closer look at British Airways. Now, British Airways is a British airline, as the name says, and their base of operation is London Heathrow, which also happens to be Europe's busiest airport. Now, British Airways, they have a fleet of more than 250 aircraft, and today they're flying to over 200 destinations globally. So this is the snapshot of British Airways. Now, British Airways, they have a very big network of destinations, as you can see here on this map. Now, most of British Airways destinations is in Europe. Within Europe, British Airways is flying to over 100 destinations, but British Airways also flies to North America, South America, Africa, and Asia. So this is the global network for British Airways, but it's also a challenge for them And the challenge is, how can British Airways reach net zero emissions in 2050 while still keeping that network? Because the easiest way for British Airways to cut down on their emission is to simply reduce their flights. But this is not something that they want to do because they want to keep a very wide network globally. So let's take a look at the emission problem of British Airways. And what you can see here is our British Airways Scope 1 emissions. Now, Scope 1 emissions are direct CO2 emissions from the operation of British Airways. And you can see that in 2018 and 2019, right before the pandemic, they regularly reach emissions of around 20 million tons of CO2 every year. Now, during the pandemic, of course, their emissions went down because global air traffic went down. And in 2022, they were still recovering from the pandemic. Now, British Airways has not yet released data for 2023, but given that the aviation sector has almost fully recovered last year, we expect that emissions from British Airways will go back to around 20 million tons per year. So this is a challenge for British Airways, is that they need to reduce these emissions all the way to zero by 2050. So how can British Airways achieve this target? There are different measures that the company can take. One of the major levers available to airlines is around efficiency improvement, essentially making your operations more efficient, buying new fuel-efficient aircrafts, and so on. But what we're here to talk about today is the really novel technologies that is available to airlines like British Airways to decarbonize their operations. From a technology perspective, there are three options available to airlines around the world. These are electric aviation, hydrogen aviation, and sustainable aviation fuel. So starting with electric aviation, how does that work? How does that work in the case of an airline like British Airways? Now, the concept of electric aviation is very similar to an electric car. It's essentially a vehicle that is powered by a battery. In this case here, that vehicle is an aircraft. Now, all electric airplanes will be powered by a battery. So how do you segment the space? The best way to segment the electric aviation sector is by looking at the type of aircraft and the markets that they are targeting. Today, electric aviation can be segmented into three different groups. The first one is air taxi and flying cars. The second one is small regional aircraft. And the third one is commercial aircraft. So what is air taxi and flying cars specifically? So air taxis and flying cars are very small aircrafts that can fly over short distances. And the key, I would say, differentiator here is the fact that these type of aircrafts are pursuing vertical takeoff and landing configurations. And the big advantage of that is that you don't actually need a landing strip, which means that these aircraft are actually very well suitable for densely populated areas. The challenge with this, however, is that you cannot fly over long distances with this aircraft, and it's a very small aircraft, so you can carry at most 5 to less than 10 passengers. So while this is an interesting technology, it's not really relevant for British Airways because British Airways is not really in the business of taxis. So the second category is a small regional aircraft. So this follows a more conventional configuration. It follows a fixed wing architecture, which means that for this aircraft, you do need a landing strip. Now, the goal of this aircraft is mostly for business travel. It's a small aircraft that can travel over short distances. And this is currently being pursued for connecting, let's say, airports to city centers, for example. Now, this aircraft can be fully electric, or it can be also deployed in hybrid configuration, often with hydrogen or with jet fuel. Now, while this is interesting, again, it's not really relevant for British Airways because British Airways is in the business of commercial aviation. They're in the business of flying a lot of passengers over long distances, which means that commercial aircraft, this is what is relevant to British Airways. Now, commercial aircraft is very much at the early stage today. This here is about electrifying a commercial aircraft, even though in most cases, the commercial aircraft will be deployed in hybrid configuration together with hydrogen or with jet fuel. Now, the goal here is not to really reinvent the design of the aircraft, so you're still using a fixed wing configuration, and which means that you would still need a landing strip. However, there's very little commercial activity in electric commercial aircraft. Today, you only have a couple of companies working on this. One of the companies active in the space is Wright Electric. Now, Wright Electric is a startup currently at the early stage, and they're now looking at launching a commercial scale electric aircraft. So right now, they're very much at the small scale. They are testing an all-electric aircraft, a very small 2 megawatt motor, but their goal, their target, is to actually launch a 186-seater commercial aircraft that could potentially fly a distance of 800 miles by 2030. So this is one of the most innovative development that is happening in the space. And as you can see in the figure, you can see the EasyJet logo. This is because EasyJet in the UK has partnered with Wright Electric in order to develop and eventually deploy this aircraft in the market. But what is the challenge with electric aviation? Why don't you see electric planes flying all over the place? The reason for that is because of the battery that you need. Now, the main challenge with electric aviation is related to energy density. And here on the figure are the energy densities of batteries versus that of kerosene, which today is used as the fossil jet fuel. Now, most commercial aircraft are relying on the lithium-ion battery. The lithium-ion battery is very good for electric vehicles, for electric cars, but it's not very good for electric airplanes because the lithium-ion battery has a very low energy density compared to kerosene. If you want to deploy an aircraft that can fly the same distance as a conventional aircraft, if you want to deploy an electric aircraft that flies over the same distance as a conventional aircraft, you would need such a big battery that the plane would be just too heavy to operate. And even if you look at the next generation batteries, like silicon anode, for example, or solid state, they also have a very low energy density. So that's the reason why it is so challenging to deploy electric airplanes. And the only way to do that would be to deploy batteries in hybrid configuration with either hydrogen or with jet fuel. But let's imagine a scenario in the future where Wright Electric has actually managed to launch their 186-seater airplane in the market by 2030. And let's imagine a scenario where British Airways has partnered with Wright Electric and they're now using this airplane, this specific electric aircraft, in their commercial operation. So what does that look like for British Airways? How far can they fly with this all-electric airplane? And the answer to that is here on this figure. With an electric airplane, British Airways could potentially fly from Heathrow all the way to Frankfurt in Germany. Now, as you can see in the figure, this is a very small range. They can't really fly very far with this electric airplane. But what's important to note here is that with this electric airplane, British Airways is actually hitting many of the key destinations in Europe. That includes Frankfurt, that also includes Schiphol in Amsterdam, and Charles de Gaulle in Paris. So these are all major hubs in the European aviation market. And if you remember, most of British Airways destinations are actually in Europe. So even if the range of the electric airplane is very small, with this electric aircraft, British Airways can actually capture quite a large share of its global destinations. So this is for electric aviation. What about hydrogen aviation? Now, there's also activity happening in hydrogen aviation. So how do you segment the space of hydrogen aviation? Now, unlike electric aviation, where every aircraft was using a battery to power their operation, in hydrogen aviation, it's a little bit different. In hydrogen aviation, you have two choices, and these choices are fuel cell or combustion. Fuel cell is where you feed in the hydrogen in the electrochemical system to produce electricity, and water is the only emission. And combustion is simply burning the hydrogen in order to produce power to operate the airplane. So, how do you use a fuel cell in a hydrogen aircraft? So the fuel cell is connected to an electric motor. Today, companies are targeting the proton exchange membrane fuel cell. It's the same type of fuel cell that is deployed in hydrogen fuel cell vehicles today. And the reason why they are targeting this particular type of system is the same as why they are using it in fuel cell vehicles, is because these fuel cells can operate at low temperatures, but they can also operate in dynamic mode. Now, companies are targeting either full hydrogen airplanes powered only by a fuel cell, but you can also deploy these fuel cells in hybrid configuration with batteries or even in combustion engines. The main challenge with fuel cell is really the operating conditions. Now, when you use a fuel cell in a car and you simply drive the car over the road, you don't really face many challenges around operating conditions. It's very different when you're flying an aircraft, because when you fly the aircraft, you go to very high altitude, which means that your conditions around temperature, pressure, and also oxygen concentration will also change. Now, these fuel cells, they have not been developed for high altitude operation. They have been developed for vehicles, which means that if you want to use these fuel cells in airplanes, you really have to take into account the impact that changing operating conditions will have on the fuel cell. Now, one company that is innovating in the space is ZeroAvia. ZeroAvia is currently at the trial stage right now. So they recently just demonstrated a 6-seater aircraft that they flew in January 2023. So this was one of the first demonstrations that we've seen in hydrogen aviation. Now, ZeroAvia is currently at the trial stage, but they have already announced their target for development. The first milestone is 2025, where they intend to launch a 19-seater airplane that could potentially fly 300 miles. And the second target is 2030, where they have a very ambitious target of flying a 200-seater plane that could fly potentially over 2,000 miles. So this company is very much at the early stage, but they have quite ambitious targets for deployment. The second option in hydrogen aviation, and the one that is really relevant to airlines such as British Airways, is hydrogen combustion. And it's relevant why? Is because of the range that you can see here. The range is very big. It's over 3,700 kilometers. Now here, it's essentially the same approach as you have in a jet fuel engine, where you rely on combustion. In this particular case, developers are relying on liquid hydrogen, where you feed in the liquid hydrogen into a jet engine. Now, even though the approach is the same, you rely on combustion, you can't simply use a conventional jet fuel engine and simply put in liquid hydrogen in it. Here you have to redesign the combustion engine. You have to develop an entirely new system in order to accommodate liquid hydrogen. And the main challenge with using hydrogen is around flame stability. So you have to make sure that the combustion profile is very stable over the lifetime of the system. Now, it's very challenging to develop a commercial scale hydrogen combustion engine for a commercial aircraft, which is why you have very limited activity in this space. But by far, the main player in this space is Airbus. So Airbus made quite a splash in the news 2 years ago when they launched their ZeroE initiative back in 2021. And with this initiative, Airbus unveiled 3 concepts, so 3 different designs for commercial aircrafts that are powered by hydrogen combustion. Now, these designs are not for small planes. These designs are for very large aircraft that can carry hundreds of passengers over long distances. Now, the designs vary in terms of the configurations of the airplanes, but the most conventional one, the turbofan plane, can potentially fly over 2,000 miles and carry up to 200 passengers. Now, bear in mind that this is a concept. This is not something that is happening today. Even though Airbus did not really disclose a timeline for deployment, we expect that if they manage to succeed in this particular space, you will likely have these aircrafts until after 2035 or 2040. So there's still a long time to go for Airbus to have something commercial that is ready to be deployed into the market. But what is a challenge with using hydrogen in commercial aviation is very much the same as electric aviation. And again, energy density is the main challenge. Now, what you see here is the volumetric energy density of hydrogen compared to kerosene. Now, compressed hydrogen has an energy density of around 5 megajoule per liter, whereas liquid hydrogen has an energy density of around 8 megajoule per liter. Now, liquid hydrogen is more dense than compressed hydrogen, which is why developers are focusing on liquid hydrogen. But still, you can see that liquid hydrogen has a much lower energy density than kerosene, and 1 liter of kerosene is equivalent to 4 liters of liquid hydrogen. So that really puts into perspective the challenge that hydrogen aviation will have in order to match the performance of kerosene. Now you can also see ammonia here. Every time we present this data, people come back and say, well, what about ammonia? Ammonia has a much higher energy density than liquid hydrogen. And they are right, it does have a higher energy density, but it's still much smaller compared to kerosene. So yes, even though ammonia has a higher energy density, it does not mean that it can match the performance of kerosene. And that's not even looking at the fact that ammonia is much more toxic, much more dangerous to handle than kerosene. So it's very unlikely that ammonia will ever be used in the aviation sector. But again, let's go back to our scenario. Earlier, we saw how with a fully electric airplane, British Airways can potentially fly from London Heathrow all the way to Frankfurt. But what about a hydrogen airplane? How far can British Airways go with a fully hydrogen airplane? Now, with a hydrogen aircraft, British Airways can potentially go all the way to Dubai in the Middle East, as well as to the JFK airport in New York in the US. Now, this is very important because with a hydrogen airplane, British Airways could potentially cover all of its European destinations, which is by far its largest market share. But it can also reach very important hubs such as Dubai as well as JFK. So with a hydrogen plane, even though British Airways cannot go all the way to the rest of Asia or to South America, it can cover a very large share of its current network. Now, remember, this is a hypothetical scenario. Airbus has not yet disclosed a timeline for the deployment of the hydrogen aircraft, and we don't even know if Airbus will be able to achieve that because it's a very challenging space to succeed. But in this hypothetical scenario, British Airways could potentially fly all the way to the US or to the Middle East with that hydrogen aircraft. So let's go to the last option available to British Airways, and this is sustainable aviation fuel. Now, sustainable aviation fuel is much more developed compared to electric aviation and hydrogen aviation. There's already commercial volumes of SAF being produced at scale today. So how do you segment the SAF space? The best way to do that is to look at the source of feedstock, what type of feedstock is being used to produce a sustainable aviation fuel. And today you can either use bio-based feedstock, which is everything from vegetable oil, from biomass, from sugars, but you can also use CO2 or hydrogen gas, and this is synthetic fuels. Now, as I mentioned earlier, this is a commercial space. It's already being produced at scale today. Now, back in 2019, not much SAF was being produced at scale because SAF is still much more expensive than fossil fuel. And in 2020 and in 2021, we had the pandemic. Not many planes were flying at the time. There was not much reason to produce a large amount of SAF. But you can see that as the sector recovered in 2022, and in 2023, you can see that the production of SAF has increased. And today, or at least last year, we produced around 500,000 tons of sustainable aviation fuel. Now, the IATA projects that by the end of this year, in 2024, we will reach a production of around 1.5 million tons of SAF. We think that it's unlikely. We think this is a bit too optimistic. The likely scenario is that production will increase, but will likely reach around 800,000 tons to 1 million tons of SAF. We think that an increase all the way to 1.5 million tons is unlikely because today SAF is still expensive, and even though the policy market is getting better with the IRA in the US and Refuel EU, in Europe, it's very likely that these policy movements will lead to such a big increase in SAF production. Now, if you look at the market for SAF, the companies developing these technologies, now what you see here are the different technology pathways to produce sustainable aviation fuel. Now, these are all different technologies that are all using different type of feedstock for fuel production. The end result is still a SAF that can be blended into fossil jet fuel. Today, there are 6 technology pathways that have been approved for commercial production and use of SAF in aviation. There's 2 pathways currently under review. There's actually more than 2 pathways, but these 2 pathways you see here, HDO, led by Variant, and IH2, led by Shell, are likely to be approved this year or very early next year. So in next year or in 2 years' time, we'll likely have 8 pathways approved for SAF production. But for an airline like British Airways, they are interested in pathways that can produce large amount of SAF in the near term. And today, you only have 3 pathways that are commercially relevant for airlines. These are Fischer-Tropsch, HEFA, as well as alcohol-to-jet. So we'll take a look at each of these pathways in more detail, starting with the only commercial pathway today, which is the HEFA pathway. So how does it work? The HEFA pathway is essentially taking bio-oil, which is either vegetable oil, soybean oil, for example, or waste oil, like used cooking oil or animal fats. What the goal here is to convert this oil into a fuel fraction with the addition of hydrogen. Now you essentially hydrogenate the oil, you refine the mixture to produce SAF, but also renewable gasoline and renewable diesel. Now, this is a fully commercial pathway. It's been commercial for more than 10 years now, which means that there's little room for technology innovation. The pathway is fully commercial. And the key focus for companies operating in this area is really around feedstock. Now, today, most companies are using first-generation feedstock, vegetable oil, but for sustainability reasons, they are looking to move away from vegetable oil into waste oil. And the challenge here is acquiring enough waste oil feedstock to supply to your entire facility. Now, this is a commercial pathway, and you already have commercial facilities. And the largest company in this space is Neste, based in Finland. Neste is currently operating 2 biorefineries, one in the Netherlands and one in Singapore, that has a combined capacity of 3 million tons of renewable fuel. Now, bear in mind that this is renewable fuel, which includes everything from renewable gasoline, renewable diesel, as well as sustainable aviation fuel. Now, even though Neste has not really disclosed how much of that 3 million tons per year is SAF, we expect that number to be very low because the market for renewable fuels today is really in the road transportation sector and not yet in the aviation sector. But essentially, if the market for SAF really increases, if the demand for SAF really goes up in the future, Neste has a flexibility of diverting some of their fuel production away from road transportation and into the aviation sector. Now, the second pathway currently in development is known as Fischer-Tropsch. Fischer-Tropsch is a thermochemical pathway where you take syngas and convert that into liquid hydrocarbon, which is then refined into fuel fraction, diesel, jet fuel, as well as naphtha and waxes. Now, the syngas can come from any source. It can come from coal or natural gas, for example, even though today no one is looking at producing jet fuel from natural gas or coal. Most companies are focused on sustainable feedstock, and in this case here, you can potentially use municipal solid waste or biomass, which you can gasify into syngas, or you can use hydrogen and CO2. This is known as synthetic fuel, where you convert the hydrogen and CO2 into syngas, and then you feed that into a Fischer-Tropsch reactor. Now, this is currently in development. Today, you only have a demo scale facility that was launched 2 years ago. And the main challenge with Fischer-Tropsch is really the cost of the technology. Both the gasification unit and the Fischer-Tropsch unit are very capital intensive, it's very expensive, and you also have the added challenge of integration. Integrating these 2 units is a very complex approach, which not many companies have succeeded so far. Now, one of the success stories in this space, and really the only one so far, is Fulcrum Bioenergy. So Fulcrum Bioenergy, they're a startup based in the US, and 2 years ago, they launched the first demo-scale facility producing SAF from a bio-based feedstock. In this case here, it's MSW. So in this case here, Fulcrum Bioenergy takes the MSW, they gasify it into syngas, and then turn that syngas into fuel. That facility is a demo-scale facility. It has a production capacity of 10 million gallons per year, although it's unlikely that today Fulcrum is actually using the full capacity of that facility. Now, what's important to note here is that Fulcrum Bioenergy is actually using the Fischer-Tropsch technology from Johnson Matthey, who is one of the leaders in this space. Now, the third and last pathway which we'll look at today is the alcohol-to-jet pathway. Now, as the name says, this is a pathway where you convert the alcohol into jet fuel. And today, the only alcohols approved for commercial operation is ethanol and isobutanol. So this is a pathway where you essentially dehydrate the alcohol into its alkene, and then you oligomerize this alkene into long-chain hydrocarbon, which you then refine into fuel fractions. Now, this is not yet commercial. This is currently in development, but the first demo facility was actually launched just 2 weeks ago by LanzaJet in the US. Now, the advantage of this platform is that on paper, it's meant to be cheaper than the Fischer-Tropsch technology, because here you're using inexpensive systems as well as catalysts. But again, this is currently in development, and it remains to be seen whether this technology is actually much cheaper than the Fischer-Tropsch pathway. But we'll know very soon, because LanzaJet actually launched the world's first demo facility for alcohol-to-jet. In this case here, LanzaJet launched a 10 million gallon per year facility in the US, where they are converting, or they will be converting ethanol into jet fuel. So with this facility, LanzaJet will be able to really optimize the system, learn from the system, and eventually use these learnings in order to scale to a much bigger capacity. And also the important thing to note here is that the ethanol that LanzaJet is using is first generation ethanol, likely corn ethanol, which is widely available in the US. Now, going back to our scenario, we've seen how with an electric airplane, British Airways could fly to some parts of Europe. With a hydrogen airplanes, British Airways could cover all of Europe as well as parts of the Middle East and the US. How far can British Airways fly with a SAF fuel airplane? Well, the answer in this case is less interesting than before, because technically SAF is almost identical to fossil jet fuel, which means that with SAF, British Airways can cover its entire network, as you can see here on this figure. Now today, the longest flight that British Airways is operating is the flight from London Heathrow to Santiago Airport in Chile. This is a 14-hour flight, and with a SAF fuel airplane, British Airways can easily reach that destination. So in this scenario, in this hypothetical future scenario, you could expect British Airways to use electric airplanes for Europe, hydrogen airplanes for Middle East and the US, and SAF for the rest of its network. Now, just because SAF is commercial does not mean that it has no challenge. There's always a challenge when it comes to low carbon technology, and there's actually quite a few challenges in the adoption of SAF in the aviation sector. The first challenge with SAF is really around feedstock, or rather the availability of feedstock. Now, what you see here is the result of a study that was done back in 2021 by the ICCT in Europe, where they assessed the potential availability of feedstock for the European aviation sector. Now, remember that the only commercial technology for SAF today is the HEFA technology. And for sustainability reasons, HEFA producers are looking at using waste oil feedstock in their operation. But as you can see here, all the way at the bottom, waste oil is actually the most scarce feedstock available for sustainable aviation in the EU. If you really want to be sustainable and you really want to have access to a feedstock that has a very large availability, then you would have to turn toward either MSW, forestry residues, or agricultural residues. And these are the three feedstocks that are applicable to Fischer-Tropsch technology. However, Fischer-Tropsch technology is quite complex to scale and also very expensive. So that's a challenge when it comes to aviation, is where do you get a feedstock that is widely available, that is abundant, but also uses a technology that is quite simple to integrate and to scale. The other challenge is related to the carbon intensity of the sustainable aviation fuel. In the case of SAF, the feedstock that you use is the one that really determines the carbon intensity of your fuel. As you can see in the HEFA pathway in the middle there, if you're using first generation feedstock, if you're using vegetable oil, you end up with a fuel that has quite a high carbon intensity. Same thing in the ATJ pathway, the alcohol to jet pathway. If you're using a first generation feedstock like ethanol from corn or isobutanol from corn, you end up with fuel that has a very high carbon intensity. If you want to have a very low carbon intensity, then you would have to turn toward waste feedstock. For example, municipal solid waste, used cooking oil, or agricultural residues. But in the case of used cooking oil, it has a very limited availability. In the case of municipal solid waste, agricultural residues, you would have to use a Fischer-Tropsch technology, which is quite expensive and complex to scale. And then finally, the third challenge is cost. It always comes down to cost at the end of the day. And that's really the reason why you don't have a lot of SAF being produced at scale today. Today, most of SAF is the HEFA type of SAF coming from vegetable oil. And you can see that HEFA made from vegetable oil is almost twice as expensive as fossil jet fuel, which means that if an airline wants to use SAF today, they would have to pay a much higher price for that fuel. You can potentially reach a lower cost SAF if you were to use waste oil, for example, but then you run into the issue of supply. If you want to use MSW, then here you have to use the Fischer-Tropsch pathway, which is expensive and complex to scale. In the case of alcohol to jet, you can potentially get a cheaper fuel if you were to use ethanol, but ethanol is a first generation feedstock, which means that you won't be as sustainable, especially if you're operating in regions like the EU, for example. So you can see that when it comes to SAF, you have a range of challenge, and each of the three technology options available today overcome some of these challenges, but none of them overcome all of the challenges. To recap, for HEFA, it's a commercial technology. It's low cost if you're using vegetable oil, and you have a strong, a robust developer landscape here. You have very good companies active in the space. However, if you're using vegetable oil, that means you are unsustainable. If instead you want to be sustainable and use waste oil, you then run into the issue of supply, of feedstock supply. In the case of Fischer-Tropsch, if you're using municipal solid waste or if you're using agricultural residues, then you are sustainable and you have access to a wide range of feedstock. And you also have very strong companies operating in the space, because this is where you have, the Johnson Matthey, the Topsoe, the Shell, the Sasol, and so on. However, there are many challenges with Fischer-Tropsch technology itself. It's very capital intensive and it's also quite complex to scale. With alcohol to jet, you have access to an abundant source of feedstock, because here you're using ethanol or isobutanol, and it's also a low-cost technology. However, ethanol and isobutanol are first-generation feedstock, which means that it's sustainable, and it also does not have many players in the space, because this space today is mostly dominated by startups like LanzaJet, like Gevo, which, even though they are good companies, they're not really the type of companies to build very large-scale facilities. So you can see that today, the options that we have for SAF are good enough for the near term, are good enough to scale the industry, but they're not perfect in order to support the global SAF sector. Now, the perfect SAF technology is the one that ticks all the boxes, is the one that has all the characteristics that you see here on the left. So is there a SAF technology in development today that actually ticks all these boxes? We think there is one, and that technology is known as methanol to jet. Now, how does methanol to jet work? Methanol to jet is essentially where you're relying on green methanol. So green methanol produced from CO2 and green hydrogen, you combine it into methanol, and you then turn that methanol into jet fuel. So methanol to jet is a type of alcohol to jet pathway, although alcohol to jet, methanol, is not yet approved. So this is something that you cannot do today. So you will have to go through the whole process of getting methanol approved as a feedstock before you go to the market. But why do we say that methanol to jet is as close as you can get to a perfect SAF technology? Is because with methanol to jet, you have access to abundant and sustainable feedstock, because if you're relying from CO2, either from direct air capture or carbon capture, or if you're relying on green hydrogen, this is widely available, or it will be widely available very soon, and it's also very sustainable. The other advantage is the technology. Alcohol to jet technology is not a very complex technology, which means that it can quite easily be scaled. The other aspect is the cost of fuel production from methanol to jet. Now, we're not saying here that methanol to jet is cheap, because as you can see in the figure, it's not. It's actually more expensive than ethanol to jet, for example. But methanol to jet competes directly with the Fischer-Tropsch pathway that is using CO2 and hydrogen. In this case here, you can see that methanol to jet is actually cheaper than Fischer-Tropsch. Now, methanol to jet is very much at the early stage today. So this cost that you see here is only an estimate. As the technology is being developed, as the technology scale, we expect the cost of methanol to jet to actually go down with time. But the other big asset, the big advantage that methanol to jet has is really the strength of its development landscape. So what you see here are 5 different companies, 5 large corporations that are each of them developing their own methanol to jet technologies. So these 5 companies have actually unveiled their methanol to jet technology last year. Here you have ExxonMobil, Topsoe, Honeywell, Total, and Accent, all of them already large players in the fuel sector today and looking at developing and deploying methanol to jet technology in the near term. So for all of these different reasons, scalable technology, abundant and sustainable feedstock, low-cost production, as well as strong development landscape, this is why we say that methanol to jet is the most promising opportunity in the SAF space today. So going back to this scenario. So here we look at how British Airways will have different options in order to decarbonize its operation. They can rely on electric, hydrogen, or SAF in order to reach net zero operation. Now, what this figure does is that it shows the range that British Airways can potentially fly with these different aircrafts. What it's not showing, however, is the capacity of these different aircrafts. And that's something that is very important to keep in mind, because this will actually be a limiting factor for British Airways. Now, what do I mean by that? If you look at today, the operations of British Airways today. So today, British Airways has 5 daily flights from London Heathrow to Frankfurt. And for these flights, British Airways is using an Airbus A321 that can carry around 240 passengers. If British Airways were to electrify this flight, then they would need 2 electric airplanes in order to have the same capacity as an Airbus 321. And the reason for that is because the right electric airplane that the company is developing can only carry potentially around 100 passengers. So in this case here, they will need 2 aircraft to replace 1 Airbus. And same thing goes for hydrogen aviation. Today, British Airways actually has 8 daily flights from London Heathrow to JFK. And for that, it's using a Boeing 777 that can carry around 370 passengers. If British Airways were to rely on the Airbus hydrogen airplane, the Airbus hydrogen airplane has a capacity of around 200 passengers. That means that British Airways will now have to fly 16 times from Heathrow to JFK in order to carry the same amount of passengers. Now, looking at this, you may think that, okay, this is inconvenient because you have to replace every Airbus, every Boeing with 2 airplanes, 2 electric or 2 hydrogen airplanes. It's inconvenient, but it's not really unfeasible, because that's something that could be done, and you'd be right. However, bear in mind that Heathrow is not only British Airways is not the only airline operating out of Heathrow. There's actually many airlines using Heathrow as their base. And in 2019, before COVID, London Heathrow actually were already at capacity. London Heathrow has a legal cap of 480,000 flights a year, and in 2019 they were almost there with 475,000 flights a year. Which means that if an airline, like British Airways for example, if they would like to deploy electric and hydrogen planes in order to decarbonize their operation, they will actually not be able to do so because there simply is not enough space at London Heathrow to accommodate these additional planes. Which is why when it comes to decarbonizing the aviation sector with electric aviation or with hydrogen aircrafts, the range matters. You have to be able to fly to your destinations, but you also have to make sure that there is no space at the airports servicing your planes, making sure there's no space for your aircraft at these different airports. So airport capacity will absolutely be a bottleneck for electric and hydrogen aviation. So what are the key takeaways from this presentation today? The first takeaway is that SAF will remain the best option to decarbonize aviation. As you've seen, SAF is a much more developed technology for net zero aviation. It's already at a commercial scale, and there's already a lot of development happening in order to further scale the industry in order to meet the demand, the global demand for net zero aviation. Electric aviation and hydrogen aviation are interesting. However, they are limited in range, but more importantly, they are limited in capacity as well. So just because you can electrify or just because you can use a hydrogen plane does not mean that you will do so in the future, because airport capacity will be a bottleneck for the deployment of these aircrafts. And finally, when it comes to the best opportunity in net zero aviation, we think that methanol to jet is the most promising opportunity, because methanol to jet overcomes many of the challenges that you have when it comes to finding the perfect SAF technology, which is a technology that has access to sustainable and abundant feedstock, a technology that can produce SAF at a low cost, and a technology that is supported by very strong companies. So this is it from me today. I hope that this was helpful and interesting, and happy to take any questions from the audience.
Yes, thank you, Renil. We'll now be taking questions that you may have on the presentation. So as a reminder, you can type those into the questions box. And if we don't get to your questions on this call, someone from Lux will be in touch after the webinar as well. So we do have a couple coming in so far, so remember to keep putting those in. The first one, you alluded to policy, but we didn't really get into too many details around policy. Do you have any opinions or thoughts on the policy landscape for sustainable aviation fuels?
Yeah, absolutely. I didn't really get into policy in this presentation, but policy is absolutely essential in order to successfully scale, especially when it comes to SAF. As you've seen before, SAF is more expensive than fossil jet fuel and will likely always more expensive than jet fuel, which is why policy is important to offset the premium of SAF and make it more economically feasible for airlines to adopt in their operation. And you have developments in policy around the world. In the US, you have the IRA that now has a credit for low carbon fuels. In the EU, you now have mandates for SAF adoption in the market. So these mandates are targeting around 10% adoption by 2030 and goes all the way up to 40 to 50% by 2050. So you definitely have development in the policy landscape for aviation, especially for SAF, and these are really essential to promote the adoption of SAF across the wider industry.
Mm-hmm. And then you referenced a policy like the IRA. I know that's spurring a lot of, I would say, projects being developed and built today. Another question here is, what is the best approach for developing a SAF project? Do you have any recommendations?
Yeah, I think when it comes to SAF, the recommendation, the first one, is really not to do everything by yourself. If you look at a successful project in this space, especially when it comes to newer technologies like alcohol-to-jet or Fischer-Tropsch, this is not something that a single company has done. I think Fulcrum is a very good example of that, where Fulcrum partnered with Waste Management to secure the feedstock. They partnered with a gasification provider, they partnered with Johnson Matthey and BP for the Fischer-Tropsch technology, and they signed offtake agreement with multiple airlines. And they did all of that before actually going to the market, building that facility and scaling that facility. So making sure that you have everything in place when it comes to feedstock technology as well as offtake agreement is very important for any SAF project. So that's the first recommendation. The second recommendation is really be careful about your choice of technology partner. We've been in this space for many years now, and from our experience, the only successful companies in this space are large corporations. This can be an oil and gas company or a large corporation like Topsoe or Accents, for example, that have a lot of experience in the fuel business. Because the reality is that SAF, just like any fuel business, is a capital-intensive industry, and it's not something that it's not easy for a startup to succeed in this space. Fulcrum, they are a startup, but they have relied on BP and Johnson Matthey in order to scale their technology. LanzaJet is the exception in this space. LanzaJet is a startup that has succeeded in bringing that technology to the demo scale. But I think when it comes to large commercial scale operation, I would much rather rely on a company like Accents, for example, who is also active in alcohol-to-jet in order to really build these large facilities. So to recap, recommendation, first, make sure you have everything in place, supply a feedstock supply agreement, offtake agreement, and so on. And two, be very careful about your choice of technology partner.
All right. Thank you, Renil. So that concludes our webinar for today. The slide presentation and recording from the webinar will be sent to all attendees via email later today. And after you leave the webinar, you'll be prompted to complete a survey on today's presentation. And we do appreciate any feedback you may have. Helps inform us and to improve future webinars as well. So take a moment and look through some of our upcoming webinars. And thank you once again for joining us. Have a great day.